You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago.
In the past 2 episodes of our show, we've been talking a lot about the geometry of space. We talked about how space itself can curve and deform, just like Einstein's theory of general relativity says it does, and we talked about how the universe as a whole is expanding. Things in space are getting farther and farther apart from each other. But what we haven't yet talked about is, well, why is the universe expanding? What is doing the stretching? So today we're going to finish this kind of 3-part miniseries and finally introduce the mysterious main character that is dark energy. So we've talked about how space curves around matter according to Einstein's theory of general relativity. And so if we make some general assumptions about how matter is distributed around the universe, Einstein's theory will tell us how space on a large scale responds to all that matter. The 2 main generalizing assumptions of this sort are that the universe is homogeneous and isotropic. So a homogeneous universe means that matter is pretty equally distributed all around. If you zoom out and look at the universe as a whole, there'll be roughly the same amount of matter in any particular patch that you choose. And the second assumption is that the universe is isotropic. In an isotropic universe, the matter distribution is going to look the same no matter what direction you're facing.
So if you take Einstein's equations and assume isotropy and homogeneity, and we turn them into the Friedman equations, and we assume that most of the energy in the universe is made up of matter, which I think, in the early 20th century would have been, taken for granted, basically. There are really 3 ways that the theory says the universe could expand over time. If the universe is spatially flat, so if it follows the laws of Euclidean geometry, then it should expand in such a way that it gets bigger at a slower and slower rate, ultimately kind of plateauing to a maximum size.
So I imagine this as a confetti cannon. You shoot the confetti out of the cannon super quickly, but then it slows down as it moves away, and eventually it all settles at some distance.
The second possibility is that you could have positive spatial curvature.
This would mean something like a spherical universe.
And in that sort of universe dominated by matter, it will be slowing down. Ultimately, you'll reach a point where it stops expanding, and then it will start contracting.
So if you're thinking about a confetti cannon in this case, eventually all of the confetti would start accelerating back towards the cannon once it settles. Maybe this would happen on Earth if you shot your cannon up towards the sky, where the confetti has to come back down eventually.
And then the third option is one where you have negative spatial curvature. And in that sort of universe, you'll expand forever and ever. It will slow down, just like in the object trying to get away from the Earth, but it will never come to rest. It will get bigger and bigger and bigger without limit.
So this is analogous to shooting your confetti cannon so powerfully that the confetti escapes the gravitational pull of the Earth and flies forever in outer space, never returning or settling. But of course, this is just an analogy. We are not talking about confetti here. We are talking about the actual size and shape of space.
All 3 of these were possibilities, and it was just a matter of going out and measuring which one our universe was. But all 3 of these involved the universe expanding at a decelerating rate. Everyone expected the universe to be slowing down as it expanded over time.
And this is just what you would expect from the confetti in our analogy. As the confetti gets farther away from us, it slows down, no matter which of the 3 cases you're in.
It turns out that which of these 3 cases you're in, the expanding forever without limit, the expanding to an asymptotically maximum size, or the expanding for a while and then contracting, which of those 3 you're in depends on how much matter there is in the universe. And to understand this, it's kind of useful to think of this quantity known as the critical density. So for a given expansion rate today, for a given Hubble constant today, there's a certain density, we call it the critical density. And if there's exactly that much matter in the universe on average, then we'll be in a flat universe, spatially flat universe that expands asymptotically to some size. And if you have more matter than that, then we will be in a positively curved universe. It will reach maximum size and contract. And if you have less density than that, you'll expand forever, getting bigger forever. So the question of how our universe has been expanding and will expand in the future had everything to do with how much matter there is in our universe.
So, for decades, the central project in cosmology was to figure out how much matter there is in the universe so that we can know how fast the universe is expanding now, but also how this expansion is decelerating over time. But eventually, things changed.
In the 1980s, two separate things happened that changed the way that cosmologists started to think about this problem. The first of these developments had to do with the proposal of the idea we call cosmic inflation. If you took the version of the Big Bang theory that cosmologists considered in the 60s and 70s, there was nothing about that theory that would lead you to expect that our universe would be very uniform and very spatially flat. It's possible, but there's no reason to have expected that. It would be surprising if it turned out that our universe was that way. But by 1980 or so, it was clear that our universe was pretty uniform. They hadn't even measured any temperature variations in the cosmic microwave background yet. As far as they could tell, it was totally uniform. It would be another decade before they measured those temperature variations, those very small ones. And secondly, it wasn't clear exactly what the geometry of the universe was, but it was looking within a stone's throw of flat. And today we know it's very, very flat.
So this poses something of a problem. Nothing in the theory says that the universe has to be flat and uniform, but for some reason, that's what we find that it is. Is this just an incredible coincidence, or is there something else going on?
So in 1980, to solve these problems and some others, Alan Guth and shortly after that others proposed models of inflation where in the very, very early universe, the universe expanded at an exponential rate. For about 10 to the minus 32 seconds, roughly, we think that the universe expanded in volume by a power of 10 to the 75. So just super dramatic expansion. So this solves these two problems in a couple of different ways. First of all, when you're done expanding, energy is dumped into space from the energy density of the vacuum. This means you should have basically the same amount of energy everywhere, and therefore the same density everywhere. And then secondly, in the same way that when you inflate a balloon, the surface of that balloon gets flatter as you progress, the universe will become more spatially flat as it undergoes inflation. So this leads one to expect the universe should be not only just approximately flat, but very, very, very close to perfectly flat. So if inflation were correct, then that really should be a prediction of the theory, perfect flatness. Now, at the time, no one knew that inflation was true, but it made some important predictions. Today, the vast majority of cosmologists think that inflation, or something very much like it, very likely took place shortly after the Big Bang. So that's the first thing that happened in the 80s that was important. And the second thing is we started to have better and better measurements about the total amount of matter in the universe. This includes both atoms and things, but also stuff like dark matter. And all of these measurements seem to come down on the side of there being a lot less matter than the critical density, maybe 10 or 20% as much as the critical density. So inflation on the one hand said we really have to have critical density of matter, but the measurements said we had way less. And this produced a kind of tension between what cosmologists theorized and what they were measuring.
And so they started to think of ideas for how to resolve this tension.
One idea they considered that was pretty popular back then, it turned out not to be the right answer, but people were imagining scenarios where there was some dark matter in things like galaxies and clusters of galaxies. This would have been cold dark matter, and this would be the sort of stuff that you could measure the presence of pretty easily. But then they also said, well, maybe there's a bunch of hot dark matter that's puffier and harder to measure the mass of. And maybe if you added those two up together, their total density would equal the critical density. But we're missing the hot dark matter in our measurements. Like that was one idea that people considered. Like I said, this turned out not to be the right answer. There's very little hot dark matter in our universe, as it turns out. But it kind of speaks to how desperate people were at the time. That was not a theory that worked very well, but still people wrote many hundreds, if not thousands, of papers on it. And then the other idea that started to become popular around the same time was one that reintroduced Einstein's cosmological constant. Now, if you recall from the last podcasts, the cosmological constant was something that Einstein put into his theory of general relativity in an attempt to make a static universe, a solution to his equations where the universe would not be expanding or contracting. Now, that didn't work, but it established that this was a logical possibility. You could include this in general relativity. And if you included a cosmological constant, what you're really doing is saying that the vacuum of space contains a certain fixed density of energy. Modern cosmologists would call this energy dark energy. So dark energy is pretty weird. Unlike ordinary forms of matter and energy, it doesn't dilute as space expands. So if I take a cubic meter of space, I put some matter in it, and then I let that space expand until it's 2 cubic meters in volume, then the density of matter in that space will go down by a factor of 2, just like you'd expect, just geometrical dilution. But if I take a cubic meter of space and I put some dark energy in it, well, there's built into it some dark energy, some cosmological constant, if you will. And then that space expands to 2 cubic meters. The amount of the dark energy in that space doubles as the space expands. It doesn't dilute. The density stays fixed. So as the volume increases, so does the total amount of dark energy. So the way that dark energy would resolve this problem is they would say, well, the density of matter in the universe might be way less than the critical density. But if you include the dark energy density along with the matter density, those could add up to the critical density in such a way that it agreed with the predictions of inflation.
So this dark energy, the energy density that exists in empty space, could add to the matter content in the universe to explain why we measure it to be so close to the critical density. But when theorists looked into this problem, they saw something kind of weird.
So if you take quantum field theory as we currently understand it, there seems to be 2 options for what the energy density of dark energy should look like. One of those options is that there should be 0. The cosmological constant should be 0. There should be no dark energy. This would mean there's some sort of symmetry built into the laws of physics, one that we haven't currently understood or whatever, but there are lots of symmetries that do this sort of thing. So it's really easy to imagine something like this might exist that sets this quantity to exactly 0. That's totally plausible. And for a long time, that's what a lot of physicists imagined was going on. But if that wasn't what was going on, then you can do a big calculation. And if you knew every particle that existed perfectly, and you knew all its characteristics, its strengths of its forces, its mass, its couplings, all this stuff, you could try to calculate how all those particles should be popping into and out of existence through the laws of quantum mechanics, and how much all those particles should contribute to the energy density of dark energy. And if you knew all those things perfectly, you could calculate it. And we can only do an estimate, but we estimate that from this sort of array of particles, you should get a energy density in dark energy that's 10 to the 120 times bigger than the critical density. That's just gargantuan. It's totally unrealistic. In a universe like that, it would look nothing like the universe we live in. So that can't be the answer. Now, of course, it's important to keep in mind that since we don't know the inputs to this calculation perfectly, our estimate might be a little bit wrong. In particular, particles called bosons and the particles called fermions kind of work against each other in creating dark energy. So you could imagine a very rare or special configuration of fermions and bosons where those 2 things cancel each other out pretty well, and you could have a smaller amount of dark energy. But that being said, if you take the naive estimate, you should find yourself living in a universe that looks nothing like ours. So at this point in history, I think most cosmologists thought probably there wasn't a cosmological constant. Some symmetry makes it go away. But by the mid-1990s, people were taking this more and more seriously. just as the data pointed more and more in that direction.
So let's talk more about what those observations were that convinced physicists that the cosmological constant was real.
So in the last episode of this podcast, we talked about Cepheids, these pulsating stars, and how they can be used to measure distances to galaxies. This is what Hubble used to make his famous 1929 measurement the universe was expanding. These can be used to measure distances because they're standard candles. What I mean by that is that you can look at some characteristics of them, like how fast they're pulsating, and deduce how intrinsically luminous they are. And that allows you to tell from their observed brightness how far away they are. This is an essential tool for cosmologists. If we didn't have standard candles, we couldn't do any kind of distance measurements over cosmological distances. Now, Cepheids are great, but they're not all that bright. So we can really only use them to measure the rate of expansion in our relatively local universe, kind of our pocket of the cosmos.
So Cepheids work to measure local cosmic distances, but to measure distances that are much, much larger than those, you need a brighter standard candle. And it turns out that you can use a kind of supernova or a giant explosion at the end of a star's life to do this.
So type 1a supernovae start with a pair of stars in a binary, so they're gravitationally bound to each other. One can be just about any kind of star, but the other one has to be something we call a white dwarf. So white dwarfs are the kind of star that our sun will eventually become when it's played out its course of stellar evolution. First, a star like our sun will become a red giant and will become very, very big, very, very bright. And then it will start to collapse, and it will eventually shrink into something about the size of the Earth, but again with about the mass of the sun. So very, very dense object made mostly of things like carbon and oxygen. It turns out that there's a maximum mass that a white dwarf can have and not collapse even further under the effects of its own gravity. This is called the Chandrasekhar mass, and it's about 1.44 times the mass of the sun. If you were to make a white dwarf any heavier than that, its nuclear fusion would reignite and it would collapse and explode and trigger a supernova, basically. So in these sorts of binary systems where we have a white dwarf and another kind of star, sometimes matter is accreted from the other star onto the white dwarf, causing it to slowly become more and more massive until it crosses this line of the Chandrasekhar mass, the 1.44 solar masses. And at that moment, or roughly depending on how fast it's spinning and other sorts of chemical questions, it will explode as a type 1a supernovae. The details of this are still very much under debate, but it turns out that if you use observational characteristics of a given type 1a supernovae, you can estimate pretty accurately its intrinsic luminosity. It turns out to be about 10 to the 44 joules that are released in just a few seconds of time. That makes one of these objects as bright as an entire galaxy for just a brief window of time. So you can see them from billions of light years away, making them extremely powerful tools for cosmologists in trying to measure distances billions of light years across the universe. So in the late 90s, two different teams of astronomers set out to measure the distances using enough type 1a supernovae to really pinpoint the expansion history of our universe over the past several billion years. One of these groups started in 1988. This was a supernova cosmology project. And then there's a second group that started later in 1994 called the High Redshift Supernova Search Team. These teams used 8 different telescopes, including the Keck Observatory and the MMT Observatory. And together they observed about 50 of these type 1a supernovae. These supernovae they were observing were exploding when the universe was only 2/3 or so of its present size. So by looking at how much light those supernovae produce here on Earth, you can learn something about how fast the universe has been expanding, not just now, but when it was 2/3 of its present size. So for the first time, you could measure not only the current expansion rate, but the rate of change of that expansion rate. And what they found was really surprising. So like I mentioned before, in a universe dominated by matter, all of the solutions tell you our universe should be slowing down. Its expansion rate should be decelerating as time goes on. But that's not what these supernovae told us. Instead, they told us the universe has been expanding at an accelerating rate over the past few billion years. And the only way we have to explain that is to introduce that dark energy, that cosmological constant, and a big one, something like 70% of the critical density. So this also had the nice feature of resolving that tension we talked about. Inflation said that the total energy density of the universe should be the critical density, but the matter density seemed to be lower than that. Well, the difference was just made up, it turns out, by dark energy. So those two teams of astronomers that made this measurement, 3 people from those teams got the Nobel Prize in Physics in 2011 for this work. Saul Perlmutter at Berkeley, Brian Schmidt at Harvard, and Adam Rees, who's now at Johns Hopkins. And they really set off a new era in cosmology. Within a few years, measurements of the cosmic microwave background had confirmed their results, showing us that our universe is spatially flat. And that in other words, that the total energy density is very close, if not exactly equal, to the critical density. And also we know that the matter density, the contribution to matter, is much smaller than the critical density. That doesn't make up the bulk of the energy density in our universe.
So the observations came in and convinced physicists that we are living in a world with dark energy, or in other words, with a cosmological constant. So it would seem like we have it all figured out. But that's only until you remember what the theorists have been saying all along.
The theorists were saying that the cosmological constant should either be 0, which now we know it's not, or it should be 10 to the 120 times bigger than it is, which it's not. So what's going on here? There have been a lot of ideas, and the answers really we don't know. There were some theories put forth early called quintessence, where it was not just a cosmological constant, but the dark energy was something that evolved dynamically. But these theories, I think, have been shown to kind of uniformly have big problems. Quintessence is not a very popular idea anymore. I won't say it's strictly ruled out, but it is big stumbling blocks it has to overcome. One idea that I'm personally very fond of to explain this goes back to a paper that the Nobel laureate Steven Weinberg wrote back in 1987. So this is a full decade before dark energy was discovered. Let's keep that in mind. So he basically suggested that you could begin to make predictions for how much dark energy there should be. He would have called it cosmological constant, but dark energy there should be in the universe if you consider not just one universe, but a large ensemble of all universes. So he says, let's imagine there's a very, very large number of universes. And it's not really important how they come into existence or something. What's important is that they're all a little bit different. Okay, so they have some of them have slightly different kinds of particles in them. Some of them have slightly different strengths of forces. They're all just a little bit different. And that means that when you calculate this 10 to the 120 number we're talking about in each of them, they'll all be a little bit different. Most of them will be around 10 to the 120 times too much dark energy, but occasionally one will be only 10 to the 119 times too much, and even more rare, 10 to the 118, so on and so forth. So the question Weinberg brings up, he says, well, as an observer who happens to be in one of these universes, how much dark energy should we expect our universe to have? Not the average universe, but one in which we are observing. So let's say we are watching, or we could look at a universe with the average amount of dark energy, this 10 to the 120 times more than we have in ours. In that universe, the universe will expand super, super fast, exponentially, it will be like inflation the whole time. And in a universe like that, no stars, no galaxies, no planets, not even any heavy elements would form. This would be a universe that life would be totally impossible in. Even if we had something like, I don't know, like 1 million times as much dark energy as we have, so not 10 to the 120, but only 10 to the 6 times more than we have, then after 20 million years or so of cosmic history, dark energy would take over and it would tear everything apart. And right now, I would say our universe is starting to be gently torn apart by dark energy. But
way to slip that in.
Yeah, I mean, dark energy is going to be rough on our universe in the long run. So far, it's gentle, but if it started really early, like 20 million years after the Big Bang, then no life could have existed. So, what Weinberg argues is that any observer that happens to find themselves in a universe has to be in one with a exceptionally small amount of dark energy. And he works out that the largest amount of dark energy that's consistent with life is approximately the critical density, within a stone's throw of that. So he says if his way of thinking about this is right, and there really are an extremely large number of universes with different amounts of dark energy in all of them, we should expect to find ourselves living in one where the energy density of dark energy is not that different from the critical density, which of course is what we've discovered a decade later. So this sort of reasoning is called the anthropic principle, and it's basically saying that any observer has to find themselves in a situation that could potentially support an observer. It's kind of a tautology. Everyone agrees that the statement as written that way has to be true, but there's a lot of controversy about, whether this is good scientific reasoning. This is the sort of way to understand our world or to make predictions. Some people criticize it because doesn't seem to be particularly falsifiable. You can't disprove a anthropic argument very easily. But I would argue that this is something that falls within the purview of the scientific method. After all, Weinberg made this statement in 1987, and he made a prediction. He said that there should be about this much dark energy, and then 1998, with the supernovae measurements, we found out that was about true. So I think Weinberg's hypothesis could be, if not proven, at least empirically supported by observations. So that to me makes it science. And I don't know if I think this is the most likely explanation for dark energy, but it's certainly my favorite.
So that's the story of how Einstein's cosmological constant, what he once thought of as his own biggest blunder, turned out to represent dark energy, this thing that we know exists and is guiding the expansion of our universe. But it's not all figured out yet.
It exists, but why it exists, and specifically, why does it exist in the quantity it does, is still one of the biggest outstanding questions in all of physics.
This episode was produced and edited by me, Shalma Wegsman. Research and writing is done by Dan Hooper and I. Dan is a theoretical physicist at Fermilab and the University of Chicago, and is the author of many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. All music in Why This Universe is produced by Jake Kleinbaum. Thank you so much for your support and for listening, and we hope you tune in next time to Why This Universe.